Welcome to Mr. Angelo's statistics class. This is topic 28 on least squares regression lines. This lesson is on the link between correlation and regression lines. Wyatt, I want to shave you. Moving on. Alright, so we looked at the idea of fitting lines to bivariate quantitative data. Right? We learned that using our own judgment as to where to place lines isn't always the most accurate way to go. We did exercises that evaluated the use of residuals or errors in the regression line to go ahead and find the perfect fit. Right? And that perfect fit turns out to be the line that makes the sum of the residuals squared the smallest possible number. So going back to the idea of correlation. Our correlation coefficient R gave us the strength of the relationship between two quantitative variables, or how well they fit into a perfectly straight line. It also gives us the slope of the regression line. So we're going to summarize that relationship with the line. It's called the regression line, where our explanatory variable is x, our response variable is y. So fairly straightforward, right? We've done this. Look at scatter plots, correlation, now we're fitting lines. So the regression line explains how response variable changes in relation to explanatory. We use the line to predict the value of y given a value of x. So we want to use that line to be able to find a value of our explanatory variable, planted it, and see what it would predict for that value y. So we need a mathematical formula different than just lines by sight, because otherwise we're all going to come up with different lines. The predicted values from our regression line are called y hat, right? You have the y and the hat. Those are the values of the y that are actually on the line. The observed values are just the y. We're going to look at that vertical distance between the points. Our y's minus our y hat. So if I have a regression line, that summarizes the points, this error, that E, or our residual, the difference between my observed y, and then the y on the line, that y hat, that would be the error in the regression line, also known as a residual. Okay? We're going to place a line, make those errors as small as possible. So our least squared regression line, or for short LSRL, is the most commonly used regression line. Puts line where the sum of the squared errors is as small as possible. So minimizes sum of the squared errors. We've looked at that before, right? And the least squared regression line, what makes it nice is we can calculate it using just the summary statistics alone. So we don't need the data as long as we have the mean of our explanatory variable, the mean of our response variable, standard deviations of each of them, and then R as well. This is typically the format that you're given on the AP test, right? Where they're giving you summary statistics, and you can use the formulas for slope and intercept. Both of those formulas which you were given on the formula sheet for the AP test. Not something you need to memorize. So here's the equation of our regression line. where here is our slope. Calculate our slope first. And then here is our y-intercept. And notice we're going to use the slope equation for our y-intercept. Remember, regression line is typically written as predicted value of y equals y-intercept plus slope times our explanatory variable. We'll use this formula today. All right, moving forward. So, regression line equation. B1, the slope of the line. For every unit increase in x, y hat changes by the amount of the slope. Always on the first response of the AP test, you'll see something about the interpretation of slope. Sometimes it's in the multiple choice, but oftentimes it says, what does this slope coefficient mean? It's been on the last couple of years as well. That's very important for determining the data, right? Interpreting that slope of the regression line. And when we get into topic 29, where we do inference for regression lines, what we're going to be doing is calculating a hypothesis test to see whether or not the slope provides meaningful information about the relationship between the two quantitative variables, similar to our chi-squared test of independence for categorical, but for two quantitatives instead of two categoricals. And then we're also going to be able to calculate a confidence interval to estimate the value of the true slope of the regression line. So that's important. The y-intercept, the value of y hat when x equals 0, usually not important for interpreting data. The values of x in your original data set usually are not close to 0, right? Depending on. All right, so here is a scatter plot of degree days versus gas usage, right? So a degree day is a measure of heat consumption, right? So in the United States, every country has their own, but the baseline is 65 degrees. So typically indoor temperatures are about 3 degrees higher than outdoor temperatures, right, to be comfortable. So that's why they do 65. So 68 is typically what people set their thermostat at to control how much gas is used. So every degree day below 65, the more gas is used, right? So for every degree it's below that mark, we'd expect more gas to be used. So if it's exactly 65, some people can be running their heaters, but not as much. Okay? So describe the form, direction, and strength of this relationship. Positive. G. What's the direction? Positive. You're right. Strength. Strong and linear, right? We're going to call this linear. So we're given summary statistics. Let's see if we can come up with the equation of this regression line. Okay. So hopefully you all have your calculators out. First, we want to do y hat, right? And remember, we're not going to be using y hat and x in these. What we're going to be using is gas with a hat on it, right? Equals, and I want to figure out this B naught plus B1 times, I'm going to do double D for degree days. So let's go ahead and first calculate our slope. B1 equals our correlation coefficient, which is quite high, times the standard deviation of what? Over the standard deviation of x. So we're calculating the least squared regression line using summary statistics.
Or drawing. This is all wrong.
And I get the slope as 0.18. Now to calculate B naught, the y-intercept, I'm going to take y bar, right? The mean of our gas usage minus, we're going to plug in that slope, times x bar, 22.31. I get B naught, negative 36.86. So the equation of my regression line, our predicted gas usage, negative 36.86 plus 0.189, that's the readings. Correction. I accidentally typed in my calculator 1.89 instead of 0.189. Let's go ahead and fix this. So 5.31 minus 0.189 times 22.31. And I get 1.09. And therefore my equation of my regression line is our predicted gas usage equals 1.09 plus 0.189 times the reading. All right, so moving forward. So the interpretation of the slope, for every 1 unit increase in degrees days, the predicted gas usage increases by 0.19, so interpreting that slope. And then the intercept, when degrees days is 0, so when it's 65 degrees outside, the predicted gas usage is 1.07. So interpreting the slope and interpreting the intercept. Generally important to interpret the slope, not so much for the intercept. Okay? We're not going to be doing any inferential statistics on the intercept of the regression. So predictions. Right? One of the easiest and most useful things we're going to do with our regression lines is to predict. Right? So let's go back and grab this guy right here and use this to make predictions. So how do you do this? So there's our regression line. What I want to do is, oh, that's the wrong one. Back again. There we go. So what I want to do is take 40, pop it in there, and come up with the predicted gas consumption. 1.09 plus 0.189 times 40. Easy enough. And our predicted gas is going to be 8.65. You guys try with 20. See if you can plug it in with 20 and see if you can get. And see what units we're into. She's 100 cubic feet. So 865 cubic feet of gas. So try for 20. See how you do on that one. Let's go ahead and plug in. Our predicted gas, 1.09 plus 0.189 times 20. And I get 4.87 for 487 cubic feet of gas. All right, moving forward. All right, let's try this example together. I'd like you to go through this with your partner. Let's take a look at this one, and we can discuss this one with your partner. I'd like you to actually try this one. So let's go ahead and go after it. All right, so plotting the regression line. So for a regression line, we've already calculated these 2 points, right? We plugged in 20 and got 4.87. Now we plugged in 40 and got 8.67 for our degree days. So what I'm going to do is just find 2 points. So whenever I want to plot a regression line, since likely we're going to be dealing with decimals, right, because we're doing real life data, find 2 points that are fairly far apart in your domain. Plug them into your regression line. Plot those 2 points. Draw a line through those 2 points. Straightforward and easy, right? All right, so properties of our regression line. If you copy down just one thing today, it would be these next couple slides. These are where your multiple choice questions come. Right? So the regression line always goes through the point x bar, y bar, right? That's kind of your pivot point where it balances. So you don't necessarily even need to plug in 2 points. You have one of the points if you have both the means, right? So the mean of our explanatory and the mean of our explanatory. That's just a point on the regression line. R is connected to the value of B1. Why? R has the same sign, B1. So since standard deviations can never be negative, right? The single thing that gives us whether or not our slope is positive or negative is that correlation coefficient R. Let me just look at R to figure out whether it's positive or negative. The values of the y variable, the response variable, is what varies, right? Regression line tries to explain the variation of y through its relationship with x, right? It's never perfectly done. Points are not exactly on the straight line. Points close to the line, the regression explains variation of y very well. Points far from the line, the regression does not explain it well. All right, so our coefficient of determination at r squared. How much variation can we explain with our regression line? R squared. So it's the percent of variation in y that's explained by the linear relationship with x. Higher values of r squared means the regression line helps explain the variation in the y variable. And forward. Residuals. Variation in y not measured by the regression line. Our formula is observed value of y minus the predicted value of y. So for each point in our data set, we can calculate a residual. So if I'm given a point in our data set, what I'm going to do is plug the x coordinate of that point into the regression line, find out what it predicts for y, and then compare those two. Right? Residuals can be negative. Notice the mean of the residuals, also another important thing for multiple choice type questions. The mean of the residuals always equals 0. Right? Why? Because the sum of all the residuals is going to be 0. Here we go. So let's calculate the point of this residual. So we have the actual point, shh, boys, the actual point from the scatter plot, 36.4. So to calculate a residual, what we're going to do is take this 30, plug it in there. All right. So we're going to have our predicted, that y hat, 1.07 plus 0.19 times 30. This will give us our predicted value for that x coordinate. And I get y hat 6.77. So now my residual, or that error in the regression line, the observed, the y minus y hat. Our observed is the actual y, and there's our predicted. So the error is 6.4 minus 6.77.
So you only plug in the first number to the equation?
Yep, that's the x coordinate. So what we're doing is we're calculating that vertical distance between the point and then what would be on the line. Okay. So we get a residual of negative 0.37. Remember, residuals can be negative. Last important part is residual plots. This is key for our inferential analysis of lines. Right? This tells us a few things. We're going to put our explanatory variable on the x-axis, our horizontal axis, and then we're going to put all of the residuals for each of the points on your on the y-axis. Right? Remember, residuals can be positive or negative. And then we're going to look at the plot. The horizontal line, any points on that line, that means it has a residual of 0. A good residual plot, you have no pattern or shape and no outliers. This will allow us to see what influential observations we have, and also will help us to detect whether or not a line might not be a good fit for a particular set of data. No. All right, so let's look at these. So I have several scatter plots here. Let's go ahead and match these up with the various residual plots. So notice, first, the easy one to pick out. Notice this scatter plot. Does a line seem to be a good fit? No, so this would match up with this residual plot B. Notice, this is what we call fanning. Right? It means the standard deviation is changing along our regression line. So our regression line becomes less accurate, in this case, for larger values of our explanatory variable. This one, right? A fairly good fit here. This is a good residual plot. So this would be A. And notice this one kind of goes up and down. This would be plot C. Right? So what we're looking for a good residual plot, no discernible pattern or shape.
So a line that would like
We know line's a good fit.
so when a line is like 0, 1, like in a sense like it's like really linear and straight, it would look like plot A.
Well, if a line is a good model, it would look like plot. This has quite a few points on this. When we're looking at it for a smaller amount of points, it'll be slightly different. All right, so a few other things on residual plots. A curve pattern, the relationship is not linear. Increasing spread about the line as x increases, predictions of y for larger x will be less accurate. And decreasing spread about line as x increases, predictions of y for smaller x will be less accurate. That's called fanning. All right, last couple. Extrapolation. The least squared regression line should not be used to predict y for values of x outside the data set. So we have to use, we can only make predictions for values of x within the domain of the original data set. It is unknown whether the pattern observed in the scatter plot continues outside this range. So whatever data we collected, we can only use those x. Last slide. The correlation coefficient and the least squared regression line are both non-resistant. Entire slide, like 3 words. 11 words.